Hello and welcome to another lecture of the course Mathematics for Economics Part 1. So, the topic that we have been covering is called differentiation. It is quite a long topic. We have covered some parts of it, and the particular subtopic within this topic that we were talking about in the last lecture is called limits. So, let us go to that particular subtopic. So, here is the definition of the limit. So, suppose a function f x is defined for all values of x near a small a, but not necessarily at x is equal to small a, then f x is said to have a limit equal to capital A as x tends to a if f x tends to capital A as small x tends to small a. So, basically what one is talking about is that take any function. Let me draw a particular diagram to motivate the issue. So, if you have a function something like this and you have a particular value of small x which is small a, then this function, the value of the function approaches this particular value capital A as small x approaches the value small a. And we have examined one particular example which is like this. Suppose small f x has this particular form, root over of h plus 1 minus 1 divided by h, and we have taken values of h which are close to 0, right. At h is equal to 0, the value of this function becomes undefined, right. Something divided by 0 cannot be defined, but as you can see, as we are taking h very close to 0, 0.01, 0.1, 0.2, etc., the value of the function approaches 0.5, right. And from the left hand side also, as this should be minus, right. As h approaches 0 from the negative side, you have minus 0.5, minus 0.2, minus 0.1, minus 0.01. The value of this function is approaching the value of 0.5. So, therefore, by this sort of heuristic demonstration, we can say that the limit as h goes to 0, the limit of this function is 0.5. Okay. Here for a general case, this limit of this function is capital A, and where can we say that the limit does not exist? Suppose you take a function like this. So, here it is defined, but suppose if you take x greater than small a, okay, then this function is actually starting from here. Okay. Then we say this limit is not there, the limit does not exist of this function at small x is equal to small a, right, because from the left hand side there you can make the value of the function to as close to capital A as possible. As small x becomes very close to small a, the value of the function becomes as close to capital A as possible, but that is from the left hand side. But from the right hand side, this is not true, because from the right hand side you cannot make the value of the function as close to capital A as possible, because as you can see that there is a gap, right. So, we say that the limit does not exist at this particular value of x is equal to a. But suppose you take a kinked sort of shape, then can we say the limit exists? So, suppose the function is something like this. Actually, here you can say that the function has limit at x as x tends to small a, then the value of the function tends to capital A. So, the limit of the function exists at x is equal to small a. So, if there is a kink like this, then there is no problem, but if you have a gap like this, then there is a problem of the existence of the limit. Now, there are some rules of the limits. So, that is what we want to start in this class. So, suppose this is given to us, that limit of f x as small x tends to small a is equal to capital A, and limit of g x as small x tends to the same value small a is capital B. Then what about the sum? What about the sum of f x and g x? As it turns out, the limit of the sum is the sum of the limits, right. On the left hand side, you have the limit of the sum, that is f x plus g x, and on the right hand side you have the sum of the limits, which is capital A plus capital B. So, this seems quite intuitive. Similarly, the second rule is, if you take the gap, that is the subtraction of f x and g x, if you subtract g x from f x and take the limit of that, then the result is same as if you take the limit of f and then from that subtract the limit of g. In both cases, x is tending to a. Thirdly, if you multiply two functions, so if you have f x and g x and take the product of f x and g x and take the limit of that as x tends to a, then the result is same as limit of f x multiplied by limit of g x. So, that will be capital A multiplied by capital B. Fourthly, if you take the ratio of two functions, then what about the limit of that ratio, and this is equal to the ratio of the limits, right, because on the right hand side you have a divided by b. What is a? A is limit of f as x tends to a, and b is limit of g as x tends to a. So, limit of the ratio is the ratio of the limits. And then you have an interesting property of power. So, you have f x raised to the power of p divided by q, and then you are trying to take the limit of that, and the result is same as you take the limit of f x, and which is capital A, and raise the power to p divided by q. Okay. So, these are the 5 sort of simple rules of limits. There are some specific functions that one can take. Okay. Suppose it is a constant function. So, suppose f x is same, it is constant, suppose it is small c, and you want to find out what happens to the limit as x tends to a, and the limit is same as the value of the function, because the value of the function is not changing in the limit also, it is the same as the value. What about a very simple function where f x is equal to x? So, this is like the 45-degree line in the first quadrant. So, if I take x only non-negative values, and this is the 45-degree line, then the limit of this function as x tends to a will be small a. The reason being that at x is equal to a, the value of the function is a. So, as x becomes very close to a, in the limit the value of the function becomes very close to small a. Okay, now we come to differentiation. We have already talked about the differentiation, but while talking about the differentiation, the idea of limit was there. So, that is the reason why we had made this short sort of discussion about limits. Now, we are back to the discussion on differentiation, and let us talk about some rules of differentiation. As we know, the differentiation of any function can be done, and this is called the derivative of this function f x, right, at any value x. So, this is called the derivative limit of h goes to 0, f of x plus h minus f of x divided by h. If this limit exists, then the function is said to be differentiable, right, and we have seen that the limit may not exist in many cases, and if the limit does not exist, then the function is not differentiable. The process of finding the derivative is called differentiation. So, there are two terms that we have defined here. One is a function can be differentiable, it may not be differentiable at a particular point, and this process of finding the derivative is called differentiation. Suppose y is equal to f x is the function, then the derivative is denoted by these notations. It is sometimes written as dy dx, it is also written as y dashed, or sometimes it is called y prime, and it is sometimes written as f dashed of x, it is also called as f prime of x. Now, what is being said is that it can be thought of as another function. So, this can be shown very simply. Suppose you have y is equal to suppose x square, then by using this definition of derivative, what you can say is that dy dx is equal to 2x. Now, this can be seen as a different function altogether. Let us call this as z, right. Z is equal to dy dx. Now, one can see that z itself is a function of x. Okay. So, that is the simple point that is being made, that if you take the derivative of a function, then the derivative itself is a function. So, now we can talk about another very simple function. Suppose f x is equal to capital A, which is a constant. Then what about the derivative? The derivative is equal to actually 0, f dash of x is equal to 0. What is the proof of this? This can be verified by two ways. You can think about the slope of the tangent to any horizontal line. So, here f x is what? F x is a. This value is a, capital A. Now, as we know, the interpretation, the geometric interpretation of derivative of a function is that it is the slope of the tangent, right, to the graph of the function. Now, if you have a horizontal line, then the line itself is horizontal, so its slope is 0. So, therefore, the derivative is also going to be 0. So, that is one way to think about it. Another way to understand why the derivative should be equal to 0 is to go by the definition, right, f dash of x, this h equal tends to 0 should be here. So, it got shifted a bit to the left. So, we know that f dash of x is equal to limit f of x plus h minus f of x divided by h as h tends to 0. Then we know f x in this case is equal to capital A. So, f of x plus h minus f of x will be equal to a minus a, which is equal to 0. So, the numerator is 0. So, which is called the, this is called the, if you remember, the Newton ratio. The Newton ratio becomes 0, therefore, it does not matter what limit I take, the f dash of x will be equal to 0. Okay, now, another function let us take, which is a constant multiplied by a function of x. So, g x is equal to capital A multiplied by f of x, right. F of x is a function of x obviously. Then what should be the formula for g of x? The derivative of g of x. Here the derivative of g of x, which we are calling as g prime x, g dashed x, is equal to that same constant capital A multiplied by the derivative of f x. Derivative of f x is f dashed x. So, any function multiplied by a constant, if I take that to be a new function, then the derivative of this new function is constant multiplied by the derivative of that function. Okay, now, another important rule, which is called the power rule. So, suppose you have f x is equal to x to the power n, right. Then what about f dashed of x? And this is given by n multiplied by x to the power n minus 1. And what is the proof of this? Okay. We can verify this by again using the definition of derivative, which is limit of h goes to 0, f of x plus h minus f of x divided by h. Now, in this case, what is f of x plus h? It should be this, because f of x is equal to x to the power n. So, f of x plus h should be equal to x plus h to the power n. Now, this term can be decomposed as x to the power n plus n x to the power n minus 1 h plus n multiplied by n minus 2 divided by 2, etcetera, etcetera. But whatever these terms are, the power of h should be 2 multiplied by something, then h to the power 3 multiplied by something, plus etcetera, etcetera. And the last term will be h to the power n, right. Now, from this I am going to deduct x to the power n, right. That will be the numerator, okay, f of x plus h minus f of x. So, from here I have to deduct f of x, which is x to the power n. So, this term becomes n x to the power n minus 1 multiplied by h plus h square multiplied by something plus h cube multiplied by something plus dot dot dot. And then I have to divide this by h. Okay. If I divide it by h, then I have x to the power n minus 1 multiplied by n, h will get cancelled, and then I have h multiplied by something plus h square multiplied by something, etcetera, etcetera. Now, limit of this will be, the other terms will vanish, all these terms will go to 0. So, you are left with only n multiplied by x to the power n minus 1. So, that is the final result, that if you take the derivative of x to the power n, then what you get is this n multiplied by x to the power n minus 1. Okay, now, there are certain rules of differentiation. So, first we are talking about the summation. So, suppose you have two functions f and g, and we know what are the derivatives. the derivatives are f dash of x and g dash of x. Then if I take the summation of them and call the summation as capital F x, then the derivative of capital F x is equal to the summation of the derivatives, that is f dash of x plus g dash of x. So, basically derivative of summation is equal to the summation of the derivatives. Similarly, if I take two functions and deduct one function from another, so you have f one function and g another function, f x minus g x is equal to capital G x, suppose. And like before, we know f dash of x and g dash of x are the derivatives of f x and g x. Then capital G dash x is equal to f dash of x minus g dash of x. So, both these results are intuitive, and how can we prove that? We can actually start from here. This is the Newton quotient, and we know if we take the limit of h goes to 0 of the limit of the Newton quotient, then we get the derivative. So, if I use this and then I use the fact that f of x plus h will be what? It will be f of x plus h plus g of x plus h, right, for the first result. And similarly, f of small x is small f of x plus g of x, right. And then we substitute these things back here, and that will give us this result by simplifying the expression. Similarly, for the second result. So, here is an example of economics. So, you have suppose what is called the profit function, which is usually denoted by pi of q. Q is the output level. So, profit function is expressed as r of q minus c of q, where r is the revenue and c is the cost, right. So, r q is the revenue function, c q is the cost function. Once the cost is deducted from the revenue, then we get profit, very simple. Now, suppose we want to find out what is pi dash q, then we use this rule here, right, this rule, and if we apply this rule here, then pi dash of q is equal to r dash of q minus c dash of q. So, how can we interpret this? The interpretation is that marginal profit is equal to marginal revenue, this should be revenue. Marginal revenue minus marginal cost. So, r prime of q is called marginal revenue and c prime of q is called marginal cost. Now, one might be interested to find at what output level the profit is getting maximized, right. The producers could be thought of as maximizing profits. So, at what output level is the profit getting maximized? That is a practical question. So, at the output level where profit is getting maximized, one can show, we shall see it later on, that level of output can be found out by setting pi dash q is equal to 0. So, if pi dash q is equal to 0, then the profit is getting maximized at that particular output level. So, this is a necessary condition. So, if this is not satisfied, then the profit is not getting maximized, as we shall see later on. Now, if you apply this rule, that is pi dash of q is equal to 0, then from this above we get r dash of q minus c dash of q is equal to 0. That means, r dash of q is equal to c dash of q. So, this is a necessary condition of profit maximization. at the output level where marginal profit is 0, marginal revenue is equal to the marginal cost. We come to another rule which is called the product rule of differentiation. So, here if you take the product of two functions f and g, and suppose the product is called capital F. So, capital f of x is equal to small f of x multiplied by g of x. Then interestingly, unlike what our intuition would tell us, f dash of x is not equal to small f dash of x multiplied by small g dash of x. It is actually equal to this. So, capital F dash of x is equal to small f dash of x multiplied by g of x plus small f of x multiplied by g dash of x. So, if we use the Leibniz notation, then this is how it looks like: d dx of f x g x is equal to d dx of f x multiplied by g x plus f x multiplied by d dx of g x. This is called the product rule. So, here is an example of how we can use the product rule. Oil is extracted from a well, and suppose it is given by x t. X t is the rate of extraction per day in barrels. So, x t amount of oil is being extracted, whereas the price of oil is given by P t, which is price per barrel in rupees. Both of these, that is x and p, they change with time. That is why they are functions of t. Now, the revenue per day in rupees will be what? Capital R t is equal to x t multiplied by P t. The amount of oil that is being extracted per day, multiply that by the price of oil, you get the revenue per day. Now, we can now use the product rule. So, we are calling it as R dot. So, R dot is dr dt. Okay. So, this is the notation that we generally use when time is involved. Here small t is time. So, applying the product rule, what we should get is R dot of t is equal to x dot of t multiplied by P t plus x t multiplied by P dot of t, right. So, what is the interpretation of this? On the left hand side you have R dot of t, which is change in revenue from oil extraction per day, right. As time changes, how much the revenue is changing. So, it comes from two reasons. First, if more oil is extracted per day, that is x is changing, x dot. Second, if price of oil per barrel rises. So, if the price itself is rising, even if the production is remaining constant, revenue will rise. So, therefore, you have this P dot term. And from this we can actually divide both sides by R t, which is the revenue, and we get this expression R dot by R is equal to x dot p plus x p dot divided by R, and that simplifies into x dot by x plus p dot by p. So, R dot by R is equal to x dot by x plus p dot by p. And in words, what does it mean? It means the proportional change, proportional rate of growth of revenue is equal to the sum of proportional rate of growth of quantity and price. Remember the derivative of R with respect to time, if I divide that by R itself, that is the expression for proportional growth of the revenue. So, therefore, proportional growth of revenue is equal to the sum of proportional rate of growth of quantity and price. The product rule can be generalized to any number of factors on the right hand side of f x. What is meant by this is that suppose f x is, instead of just f small f and small g, I take this as a of x plus b of x plus C of x. Suppose only 3 functions are involved, right. So, you do not have 2 functions on the right hand side, but 3 functions of x. Then what happens to the product rule, right. Here the product rule will be the following: you take A, this is the first term, okay. So, you are taking one derivative at a time. Out of the 3 functions, you are taking derivative of one function at a time and keeping the others as functions itself, they are not differentiated. So, you are going to get 3 terms on the right hand side. The proportional growth rate of a variable would be likewise be the summation of proportional growth rates of individual factors. So, if you have something like this, that f of t is equal to a of t, b of t and c of t, right. And suppose you want to find out this, right, the proportional rate of growth of f, then what is being said is this will be equal to this. So, it is basically summation of 3 terms. Each of these terms denotes the proportional rate of growth of each of these functions, 3 functions on the right hand side. Okay, here is another example where we can use these rules, the product rule. Suppose dP, which is the demand for a good whose price is given by capital P. So, D is demand, P is price, D is a function of price. The revenue earned by the producer will be Rp. So, Rp is how much you are selling multiplied by the price of the good, so that is revenue. How much are you selling? That is given by the demand, because people will be demanding and that is why you will be selling. So, Rp is equal to D of P, which is a function, multiplied by the price, which is P. Now, we can use the product rule here. So, R prime of phi will be given by this. So, what is the thing that is going on in the background? I have jumped one step. This is basically D of P multiplied by the derivative of P with respect to P. The derivative of P with respect to P is 1. So, nothing is coming here, plus P multiplied by the derivative of the demand function with respect to price, which is D prime P, right, P multiplied by D prime P. Or we can take dP common on the right hand side, and what we should get is 1 plus P multiplied by D prime P divided by dP. Now, this term is an interesting term. It is let me write it separately. It is P D prime P divided by D of P. It has a special significance. It measures the proportional change in demand with respect to proportional change in the price. It is called the price elasticity of demand, right. So, what is this term? P multiplied by D prime P. D prime P is the change in the quantity demanded with respect to instantaneous change in the price, and whole thing is divided by the quantity demanded, which is D of P. So, this is called the price elasticity of demand. Now, there is something called the law of demand, by dint of which the D prime P is negative, which means if price rises, the demand actually falls. So, D prime P is negative. So, the above expression is generally negative. The above relation establishes that if revenue rises or falls with respect to change in the price, it crucially depends on the values of price elasticity of demand, right. So, if I take the absolute value of this, right, it is negative, but if I take the absolute value and if it is greater than 1, then this whole expression will be negative. So, that will mean that if price rises, then the revenue will fall, or if price falls, then the revenue will rise. So, whether the revenue rises or falls with respect to price, it crucially depends on the expression, this expression, the price elasticity of demand. Okay. Now, we come to another rule, which is the derivative of a quotient. So, if f and g are differentiable at x and suppose g x is not equal to 0, then capital F, which is equal to small f by small g, it is differentiable at x, right. Now, if it is differentiable, then what is the derivative? So, that is given in the next line. So, we have capital F x is equal to small f x divided by g x, and capital F dashed of x is given by this expression, f dashed of x multiplied by g x minus f x multiplied by g dashed of x divided by g x whole square. In words, the derivative of a quotient is equal to the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. This difference is divided by the square of the denominator. Okay, that is the explanation in terms of words. So, we take one example to actually grasp what is going on here. We take an example where f x is equal to 3 x plus 7 divided by x minus 5. We have to find two things, f dashed of x and f dashed of 2. So, if I can find out f dashed of x, then that is a function of x. We have seen that the derivative itself is a function of x. So, to find f dashed of 2, I just have to replace x by 2. So, the first task will be to find f dashed of x. So, we use the quotient rule, we get this. So, in the denominator you have the square of the denominator of the original function, which is x minus 5 whole square, and in the numerator you first have the denominator x minus 5 multiplied by the derivative of the numerator, which is 3, plus the numerator, which is 3 x plus 7 multiplied by the derivative of the denominator, which is equal to 1. And then we simplify this, it becomes 3 x minus 15 plus 3 x plus 7, and that turns out to be 6 x minus 8, and obviously this is going to be divided by x minus 5 whole square. So, we have found out what is f dashed of x, but there is another part, which is we have to find out what is f dashed of 2. That is easily found out by replacing x by 2. So, if we do that, then on the numerator you have 12 minus 8, which is 4, and divided by 2 minus 5 whole square, which is 9. So, therefore, it becomes 4 divided by 9. Okay. Again, I talk about another example from economics. Now, we know there is this thing called the cost function C of x. X is the output, C is the cost. The average cost is given by C x divided by x. Okay. Basically, we are dividing the cost function by the quantity produced. that gives us the cost per unit of output, and that is called the average cost. Now, one might be interested to find out the derivative of the average cost, right, and here the independent variable is the output level. So, we have to take the derivative of the average cost with respect to the output level. Now, we use the quotient rule. So, this is the, on the left hand side you have the ddx of Cx divided by x, and if I use the quotient rule I get this expression x multiplied by C prime of x minus Cx divided by x square. Now, let us simplify it further. So, if I simplify it a little bit, it becomes 1 divided by x whole thing multiplied by C prime of x minus Cx divided by x. In other words, the average cost rises if the marginal cost is greater than the average cost. Why am I saying this? Because this first expression, if you remember, this is called the marginal cost. We have talked about this before, and this itself is average cost. Right. So, ddx of the average cost is equal to 1 divided by x multiplied by marginal cost minus the average cost. So, if it is the case that marginal cost is greater than the average cost, then the right hand side is positive, and if the right hand side is positive, then the left hand side is positive, which means that as output level rises, average cost is rising. Similarly, if marginal cost is equal to the average cost, right, if the marginal cost is equal to the average cost, then on the right hand side you have 0, and if it is 0, then the ddx of average cost is equal to 0. That means the average cost does not change, it remains the same. And finally, if marginal cost is less than the average cost, right, then from the right hand side you are getting a negative expression, marginal cost is less than the average cost. In that case, the left hand side is also negative. That means that the average cost is declining as the output level is rising. Okay. We will see that these things are quite important if one talks about what is called the theory of the firm. Okay, now we can also talk about proportional change. Here, suppose you have a function f of t, capital F of t, which is equal to m of t divided by n of t. So, both m and n are functions of t. We use the quotient rule here and we will get this expression that ddt of f t is equal to m dash of t divided by n t minus m t divided by n t multiplied by n dash of t divided by n t. I have jumped some steps here, but this is what you are going to get by using the quotient rule. Now, from the above expression, then I divide both sides by f t and I will get this expression, because f t is equal to m t divided by n t, and then I multiply this term with the terms in the third brackets and I will get this expression, and which means that f dash of t divided by f is equal to m dash of t divided by m minus n dash of t divided by n, or in other words, since f dash of t is equal to f dot t. So, f dot t divided by f t is equal to m dot t divided by m t minus n dot t divided by n t. So, if I express this in words, if a variable is the quotient of two variables, then the proportional rate of change of the variable is proportional rate of change of the numerator minus the proportional rate of change of the denominator, right. This is the proportional rate of change of the numerator and this is the proportional rate of change of the denominator. You take the difference of these two, you get the proportional rate of change of the ratio. This relation is again quite important in economic analysis. So, for examples, there is something called the real wage rate. So, small w t, it is the ratio of the money wage rate and the price level. So, suppose capital W is the money wage rate and capital P is the price level, right. Then the real wage rate is defined by this. So, small w t is equal to capital W t divided by P t. So, the total amount of money people are getting as wages divided by the price level, that is called the real wage rate. Now, we can use the rule here that we have just got, then we should get the following expression. In words, what we are getting is that the proportional rate of change of the real wage rate is equal to the proportional rate of change of money wage rate minus the proportional rate of change of price level, right. And this is not very difficult to understand if you think about it intuitively. The real wage rate of the workers, suppose, what does it mean? It means the purchasing power, right. We are dividing the amount of money that they are getting by the price level, right. Now, that real wage rate can rise because of two reasons. One is that the money that they are getting, that is rising, okay, or it is possible that price is declining, okay. So, in both cases their real wage rate will rise. So, that is why you have the proportional rate of change of the real wage rate is equal to the proportional rate of change of the money wage rate minus the proportional rate of change of the price level. So, it also says that suppose the actual money that the people get is constant, that is not changing, but the prices are rising. In that case, on the right hand side this will be equal to 0, but this is positive. So, the entire term becomes negative, okay, which means that in that case the real wage rate of the workers will be declining, and this is quite intuitive. Okay, we shall start with this topic in the next lecture, partial differentiation. So, we have today covered the topic of differentiation proper. We have not talked about partial differentiation, and we have talked about different rules of differentiation, the summation of two functions. If we take the derivative of that, then what happens? If we take the product of two functions and take the derivative, if we take the quotient of two functions and take the derivative, then what are the expression that one is likely to get? We also talked about power rules, we talked about the derivative of a constant term, etc., etc. And let us call it a day. So, I shall see you tomorrow with another topic, which is partial differentiation. Thank you.